that the algorithm can detect and see whether these different groups actually correlate with the price in any way.
I mean, even if we don't get anything out of the clustering, using some kind of language model is a kind of semi-supervised learning, where the model tries to learn words based on the other words that are within the document itself.
Interesting. So, based on your experience, right, other than, let's say, doing unsupervised learning on financial assets, what are the typical usage of unsupervised learning that you can think of?
So for our assignments early in this AP program, one of our assignments was to look at association rules in
This is for e-commerce.
Yeah, e-commerce like a stock list lah. So you're trying to find different items that customers buy to show that they are related to one another in terms of consumer habits. And because you don't have any label, so you're just trying to find some relationship between possible relationships between different items in the inventory, and possibly with the information you can choose to either increase price for one thing or offer a promotion on one item but not on the other item, and you still get the same kind of effects. Yeah.
I think this kind of thing is also used for recommender systems, like finding out which items people of a certain background buy, and like you could recommend them other items that you think they might be interested in. So there's quite a bit of e-commerce applications.
Yeah. And I think this is where it gets very interesting, because usually for supervised learning, there's already a label, right? So you can roughly tell how well the model is performing. But for unsupervised learning, right, let's say they tell you that, okay, the ideal number of clusters to form is, let's say, 4. But once you have that 4 types of cluster formed, without any specific domain knowledge, for instance, let's say you are working in Lazada, if you have identified that there are 4 main clusters of customers who shop regularly there, without further domain knowledge, right, will we be able to identify anything about what do you think? Like, without any specific domain knowledge, are you able to make sense out of the clusters?
I think domain knowledge is very important. Because if not, you just got some groups and you don't know what to do with it. So you do need to speak to someone who's very familiar with the domain, and they can maybe help you understand what your algorithm is doing. If not, it's just, these are a bunch of products that are in a group together, but why? Maybe someone there needs to, you probably need someone with domain knowledge to really help you understand and kind of make sense of what the outputs of your algorithm are doing. So it's not, I mean, you cannot discount the value of domain knowledge for this, I think.
I think it's important to develop a kind of assessment strategy, especially when you use unsupervised learning. Because supervised learning, you already have the labels, but for unsupervised learning, you don't. So if you're able to define some kind of assessment strategy, just to see like whether it makes sense, or to see whether your clustering or your unsupervised learning is good or not, that helps. And if you design it well, then you are able to kind of have a check and balance system on your unsupervised learning. If not, even if you get the results out from your algorithm, you might not be able to make sense whether it's a good or bad model.
And speaking of a good and bad model, so how do you actually evaluate what is the right model to use for unsupervised learning? Because there are many, right? Like for supervised learning, they say like random forest, decision trees, SVM. Then for unsupervised, you've got like K-means, GM, things like that. So then the question is like, how first do you decide which is a good model to use? And once you have decided on a model, how do you evaluate whether the performance of the model that you've chosen is good enough? Yeah. So Deepan, you want to share on how do you actually choose the first model to implement?
Okay, in general, I think for machine learning, you always start with the simplest possible one you can implement. Just get your baseline results out, get something that works quickly out as possible, and then from there you iterate. Like, I don't think it makes sense to spend like too long trying to evaluate, like, unless your problem has very specific characteristics that are best solved by a certain algorithm. If it's like a kind of a general problem, always go with the simplest, and then you can always iterate from there. I think this holds true in general to programming and like to machine learning as well. Like, don't spend too long in that cycle of like trying to decide, oh, what should I start with, or get something out first and then iterate is a lot better than getting stuck with that kind of problem. Yeah.
And what about you, Kajun?
I think I'm trying to understand the problem and frame it as a data science problem is very important, because then you will know what you're trying to achieve in terms of at least the concept behind your problem. For example, let's say you want to be able to classify for data, like whether the person has cancer or no cancer, right? So then you know it's a supervised problem. So you can narrow down what kind of algorithms you use, and then you think, well, maybe okay, this problem is it linear or non-linear? If you think that okay, it is most likely non-linear, then it's better for you to start off with algorithms that are machine learning algorithms or supervised learning algorithms that are non-linear. Then from there, you can actually narrow down what kind of algorithms to use. And if you are good enough in your math, then understanding the problem will also help you choose the correct, for example, loss function. Different algorithms have different basis or principles of how they work. For example, logistic regression, you're trying to fit it in the logistic loss, right? And for SVM, you're trying to draw a hyperplane, but both of them are linear classifiers that try and maximize or minimize the classification loss of your data, right? So then thinking about how you are able to fit, thinking about how your problem is related to what kind of loss function or what kind of thing you're trying to minimize, it will help you choose the right algo better.
And depend just a bit on your point. Just now you're saying that you should start the simplest model.
Mm-hmm.
So based on your understanding for unsupervised learning, right, what is the simplest model in your definitions?
For clustering at least.
Yes.
K-means is probably the easiest one.
Yeah, K-means. I don't know about you, Kajun. Any?
For me, it depends on the problem. If you are very sure the number of clusters that you want to choose, then I guess K-means is a good starting point. And if you know, like for example, K-means is bad at outliers, and if you know your data has a tendency to have a lot of outliers, then maybe you want to avoid K-means. Or if you feel that your clustering has a soft boundary instead of a hard boundary, then you might want to try Gaussian mixture models. If you know for sure that your data has hard boundaries in your clusters, then maybe you can try, K-means or even hierarchical clustering, or you might want to try DB-scan. If you know that your clusters are most likely clustered by density, for example, rather than by attributes.
Yeah.
I mean, partly also because, we're kind of talking about this in kind of a solving a problem kind of approach. Like you already know that you want to cluster for some reason, but I think clustering is also used a lot of times just for data exploration. Maybe you've got some new data and you're not quite sure what to do with it yet. I think clustering is pretty useful at that stage as well. The early stages when you're just doing exploration, you're trying to figure out is there am I missing things, like you have a million data set, you can't look through it and figure out like what's going on there. You do need to run some kind of exploration. You do your plotting, and it's one of the tools that can be used at that stage as well. So it might be even before, it might not be part of your actual problem solving step. It might be understanding the problem step. It can be very useful at that stage too.
Yeah. So to build on their points, right? So what you're seeing right now is a page on sklearn. Hang on, let me do a reshare. Anything?
Let's see.
Hang on, I'm sure to share with you a screen. I'm facing some technical issues. Hang on.
Can you share your entire desktop?
Okay, great. Okay, so what you're seeing right now is a page from sklearn, right? Our best friend for data science and machine learning. So if you look at it here, right? So what they do here is a very nice illustration of all the different algorithms that you could use. Like for example, K-means, and GAM, the most of the common one, and the type of classifications they will form based on how the data are being distributed. Of course, this is a flattened image, right? So you know that by now you should be aware that every columns or every features that the data has is an additional dimension. So what they are showing here is that they flatten everything into like 2 dimensions, so that you're able to visualize it, right? So you look at here, right? Like k-means, right, is very bad if you are going to do a classification for this kind of data distribution, because it will just split the data into half. But if you look at it just by eyeballing, right, you know that the inner circle should be one cluster potentially, and the outer cluster should be another cluster. So you can see that this is where like the DBS scan, like hierarchical clustering, and other kind of methods might outperform. But if you look at other like distribution, like if the data is spherical in nature, then k-means will tend to give you a very good result, right?
Yeah. So the reason why is because k-means you are working with centroid, and you're working with spherical shaped clusters. So of course, if you use this, if you see this, you can't really draw 2 spheres, right? But what happens in this k-means is you have kind of like one sphere here and kind of like one sphere here. And for this one, it's kind of like one sphere here and kind of like one sphere here. So the algorithm works by trying to create like the most well-defined like spheres, right, or circles if this is 2D, and so that's why it fails. So it's important to know like what shape your data is, or at least if you can have certain assumptions about your data that you know, okay, it's good, you can cluster it in the spherical form, then okay, then k-means makes more sense.
This is quite actually, this might be a good example of like really understanding like what's going on in your data, because actually like I guess this is like XY coordinates, but for at least the first example, if you know it's in this shape and you transform it to say radial coordinates, you will probably get very good results. So like doing you sometimes, like if you understand what your data looks like, you might be able to do data transformations on it such that certain algorithms work better.
Yeah. So I guess another questions that most people have is that how, okay, let's say you want to use k-means or GAM, right? One of the key inputs that we need to give is how many clusters to form, like number of components or number of clusters, right, for k-means. So how do you usually go about deciding how many clusters to form by the start? Is there any thought process or any kind of a metrics you use to guide you through this?
If you, for example, if you already know how many clusters to choose in your problem, like you want to find like 5 different kinds of customers or 4 different kinds of customers, then maybe you choose a clustering with like k equals to 4 or 5. But if you don't really know, then k can become like a hyperparameter to tune. Yeah, and then you just have to do it with some research.
Yeah. So just a bit on that point. So for instance, let's say if your business unit come to tell you that you can use based on their industry knowledge, that usually like 3 main groups of customers. So potentially you can start from there, right? But maybe you might think that maybe the business person might not know his stuff that well. So you can do a 2 clusters, 3 clusters, and 4 clusters, just to bring out the data to see whether having like 3 clusters makes sense or not. So I think this is how you can start. And is there any metrics you think you can use to help us guide us on that? Let's say, for instance, the business is new, they have no knowledge on that. Do you think is there any like score or like any kind of graph you can plot to see what's the ideal cluster so far?
I think it should be the other way around. You might need to speak to your business side stakeholder to kind of understand what the problem they have is first. It doesn't make sense. It doesn't, unless you're doing data exploration, but you're actually trying to solve like a business problem. You really need to work very closely with your business stakeholder to kind of understand what they're trying to solve, and then from there you kind of work towards, oh, you're trying to solve this problem, therefore maybe it makes sense to have this number of clusters and that kind of helps you segment your inventory correctly or your customers correctly or whatever it is they're trying to solve. So I don't think there is quite a general rule for like this, start with this many. I think it's a lot to do with specific problems and understanding exactly the kind of business value you're trying to. I mean, if it's a business problem, if you're just playing, then just try everything else.
Yeah. How about like using metrics like rate score or things like, for instance, plotting hierarchical clustering. Then from there you decide how many clusters. Do you usually do this in your project as well, like using like rate score or like do hierarchical clustering to see what the main clusters that they identified before you use number of clusters?
If you look at the sklearn clustering page, you also can see that there's this clustering performance evaluation, and then it's a mix of evaluations where you actually know the clusters that the data point belongs to, and if you don't know. So if you know already, then you can use some of the methods here, but you have to realize that it becomes almost like a supervised problem already. But if you don't know, then you can use, for example, silhouette scores or the.
It's way bottom. I think at the bottom. Silhouette score, I think is at the bottom.
Here you go.
Yeah.
Which tries to measure the. They all measure around the same thing, like the mean distance between sample and other points of the same class, and sample points of the next nearest cluster. So, I mean, essentially clustering, you're trying to minimize the cluster distance and maximize the inter-cluster distribution. So this is the kind of measure that you usually use. But having said that, having these scores might not reflect accurately the quality of the clusters. What Dipan said is, I think is very true, that you really have to consider, like in the business sense or in the application sense, how many clusters is best for you. So if you approach it in the machine learning sense, it becomes a hyperparameter to tune yourself. But if you think about it in a physical sense, it will help you decide, how many clusters to use. I mean, this is generic for most machine learning problems. For example, what kind of the machine learning algorithm to use even is also, you should also think about it in a physical sense first before deciding on which one to choose.
Yeah. So let me just do a quick recap here. So based on our discussion so far, we have discussed on the number of clusters you can use to form, and usually for you to determine that, you need to have a very strong domain knowledge or the business knowledge, right? And the way to get this is by talking to your internal stakeholders, because at the end of the day, they need to make use of whatever data that you have provided with them to make some decisions. Like for instance, let's say if they think that there are 3 clusters, so based on the 3 clusters, they can do 3 separate marketing campaigns to target some customers, right? So they have already 3 clusters in mind. So if let's say if you use like rate score to give them, to try to identify the number of segments mathematically, but maybe they say, okay, the number of distinct clusters should be 5, that's the optimal. But then your business stakeholders think that there's 3. So we're going to present to them that, hey, there's 5. It might be very hard to get their buy-in, right, in terms of how should they run the marketing campaigns, right? So ideally, this is a very iterative process, right? For instance, let's say if you identify, if they think that there's 3, but you identify there are 5, then there could be some additional insights that you could have obtained through running through data, which they might not be aware of. So who knows, right? They might change their marketing campaign strategies from 3 segments to 5 segments, or they might tell you that, hey, the 5 is not correct because of certain, let's say, industry regulations or a certain like industry law that prohibits to target specifically that 2 groups of audience, for instance, right? So it now becomes 3. So there could be some additional background knowledge that you might need to have. And the best way to do this is to engage your internal stakeholders constantly and throughout the process of this data cleaning and data analyzing process, so that you don't give them a surprise at the end of the day, right?
Yeah, you should work actually you should work with your other stakeholders to understand if for example, your clusters make sense or not. For example, if you choose an arbitrary number to say you have 5 clusters and you use the agglomerative clustering, for example, and so you present your results to the experts or the people with domain knowledge that you work with, and you say, okay, you work with people who are familiar with customer consumption, the customer behavior, and then you say, okay, so these are the 5 clusters. This is a characteristic of each cluster. Okay, this cluster has a spending range of this much. That cluster has a spending range, a different spending range. Or this cluster is interested in this kind of products, and that cluster is interested in this kind of products. And you share with them the results that you have, and they can tell you whether it makes sense according to your intuition or not. And if it really doesn't make sense, then actually it's better to listen to these domain knowledge experts and revisit choosing another for example, number of K, or fine-tuning your model if you use a different model, or change the hyperparameters of another model and bring it back to them and to see if that actually makes more sense. And if it makes more sense, then maybe you actually have improved the quality of your unsupervised learning in that sense.
Yeah. So that should give you hopefully through that discussion that we had earlier, it gives you a wider perspective of unsupervised learning, right? Because on data camp, it's very prescriptive, right? They tell you, okay, iris data set, okay, then do unsupervised, then you can identify 3 flowers, for instance. But in real life, it's not as simple because iris data set, you know beforehand that there are already 3 types of flowers, right? But in an actual world, there could be many more segments and the data is more messy. And it's not as simple as someone giving the instructions of running 3 clusters. They might come to you and say, hey, I don't know how many clusters or customer segments that do I have. Please tell me. Right? So things like that. Right? So next, I think we move on to on some of the sharing that we have. So based on whatever you have shared earlier, do you have any kind of like personal side projects that you're doing, or any kind of additional insights that you want to share with the participants here?
Okay. For me, my PhD topic was actually, one of the projects was on classifying lung recordings, like breathing recordings that have excessive lung water versus recordings that don't have excessive lung water. So the medical condition is called pulmonary edema. So what we do is you just record, like using a stethoscope sensor, the person's breathing, see whether this person has like excessive water or not in their lungs. So it's a classification problem, but in the audio domain. So what the features we used was the magnitude spectrum of the audio signal. But the catch is that we tried to improve current methods in the presence of noise. So we have recordings that have like background noise, like people talking or machine beeping and things like that. So using conventional methods such as logistic regression, right, or SVM, did not produce robust methods that could classify these 2 classes in the presence of noise. Without the presence of noise, that means the clean signal was very good. But once the noise came in, it messed up with the learning. So what we used for that was the non-negative matrix factorization algorithm, which essentially tries to take your data, which is a matrix of features and samples, and tries to split it into 2 different matrices, where the number of the matrix size is arbitrary, that you can choose yourself, which is what we call the number of basis vectors, which is K, right? And so it is an unsupervised learning method because there are no labels. Even though my project was supervised, we process the data using unsupervised methods to see if what we call the dictionary that we learn, that means one of the matrix will be called a dictionary, and this matrix that we learn is robust to noise or not. So using non-negative matrix factorization, you are able to learn the shape of the data, the audio data for breathing sounds, and we also can learn the shape of the audio data in the sum of matrix form for noise. And then being able to use these two separate information, we were able to increase the classification score in the presence of noise. If you want to know more, you can actually read up on non-negative matrix factorization, which is a generalized version of PCA.
So interesting. So you mentioned last sentence that PCA. So so is PCA also unsupervised learning itself?
Yeah. So PCA, what you have is a loss function that tries to transform the data so that the variance is maximized between each feature. So you have new features for the data, and these features have maximum. You try to maximize the variance between all the data points for the original features that you have, and transform it to a new space where it has maximum variance.
What cases would you decide to use PCA for? Like, why would you want to use PCA?
Because usually, you can use PCA if you want to reduce your dimension, so dimensional reduction. So let's say you have 1,000 features, right? And you want to see if all 1,000 features are useful. If you think that not all 1,000 features are useful, you can use a PCA transform and choose features that contribute to maybe 90% or 85% of the total variance of your data set, and the rest you can disregard, for example. And sometimes out of 100, maybe you only use maybe 50 or maybe 40 or even fewer, and that helps reduce the number of features. First of all, it will help you run your supervised learning algorithm faster, for example, logistic regression. Two, you reduce the number of dimensions so that it reduces the effect of dimension, the curse of dimensionality, right? And it may increase your classification score.
Yeah, interesting. So you mentioned that using PCA, they help to narrow down the number of features. So, Deepan, do you think that by doing PCA, it can also help you to do some feature selection, like for example, identifying what are the key or most important variables that you should look at when you are doing some predictions?
I mean, you do basically when you have a data set, you want only descript like features which are informative. There's no point like if you have two rows of exactly the same data, right? You're just adding computation and not getting anything out of it. So I mean, PCA is definitely something you should explore. Again, like with a lot of machine learning, it's a lot of it's art rather than science. So you might not beforehand really know what would come out of it. It's one of the things that you try and see whether what kind of results you get out of it. And I mean, if you can reduce the dimensionality and without like a significant drop in accuracy or within your acceptable limits of what your accuracy needs to be, then why not? Yeah, there's no real downside. You're getting faster computation with a smaller with basically a more descriptive data set.
Yeah. So to add on that point, so right now on my project, I'm doing a project on using AI to predict the clinical complications of patients, right, before they even develop. So you can imagine that, let's say right now, when a patient go for some treatments, right, usually they'll take the blood pressure, the weight, everything. If there's an AI who can help to predict what kind of complications that could happen, given the changes in the patient's medical parameters, then potentially the nurses and doctors will be able to take preemptive actions, maybe through educations or medications, to actually help to minimize or prevent the complications from developing. So you can imagine like in a blood test, right? I mean, there are like maybe 10 or 20 components in your blood. Then there are so many other parameters like your weight, your height, your education, your marital status, your religion, everything. So all these are in the patient's data set, right? So when I go to talk to the stakeholders, right, definitely I won't tell them that, hey, based on these 1,000 features that you give to me, this is the accuracy. Definitely the key questions they'll ask is, so what are the key things that the nurses or doctors should look out for? Or what are the key medical parameters changes that could help the nurses to predict patients' developing such complications, right? So this is where what people mentioned is important, where you do a PCA to identify what are the key changes in the parameters that the doctors should look out for to get their buy-in. Because developing a model is relatively easy, but getting the stakeholders to believe in your model and to act upon it, I think that's a total challenge altogether. Can you imagine you go to a doctor and like, hey, okay, if the machine flash red, you should administer the patient to the hospital. Being a doctor, they will definitely try to understand why. Like, why should I trust your machine? What if it's like a false positive? Like, so I am sending the patient to the hospital, but without knowing the reason why. So this is when, by using PCA, you can narrow down and tell the doctor that, hey, if the systolic blood pressure changes by 10 over the past 1 week, there's like 80% chance that the patient will develop some complications. Then at least the doctor, based on his medical knowledge, he can verify this fact that picked up by the machine learning, say, hey, actually what you say is correct based on my medical knowledge, right? If the blood pressure dropped by 10, potentially there's some like blood infections or some like disease of the heart. That's why the blood pressure drops so much within a week. Then it makes sense to the stakeholders, and it'll be easier for you to get their buy-in, to believe in the model. Because if you spend a month developing a model and it's not used by anyone, your effort just goes to waste.
Sometimes spending time with your stakeholders is more important than spending time building your model. Because in the end, I mean, what you're trying to do is you're trying to solve real problems, right? I mean, unless you're just doing this as an academic exercise, so it's a different issue. But if you actually want to, if your aim is for this to be a career and for you to solve problems, spending more time in front of your computer is not always the best way to solve problems.
Yeah, and if there are two models, like, I think, believe it or not, if there are two models, one model, the accuracy of performance is 80%. The other accuracy of performance is like 75%. So logically, if you present two models to the stakeholders, they might choose the 80%, right? But if you are able to convince them on why the machine is giving such predictions and what are the key features you should look out for, they might instead adopt the 75% model instead of 80%, right? I think one of the very famous case for this is the Netflix competition. The Netflix competition.
I've heard of it, but I'm not familiar with the details.
Yeah, so basically for the Netflix competition, what I did was the Netflix trying to improve the movie recommendations for the customers of Netflix, right? So I think in the competitions, right, there are two trends that have developed. One is that it's an ensemble of all other models. So basically, it's the loser team. So what they do is that they say, hey, since the number one in the team, right, in the league, is raised, the score is very superior than ours, why not we do an ensemble of all the models? So if your score is lousy, just pass me your code, I put inside model. So example, you combine them together to see how much the score improve. So so this is one group approach, right? They take other models and build into theirs and try to beat the number one. So the other one, the number one team, what they do is that they still keep it very exclusive. It's only like 3 or 4% in the team, and they develop the model by themselves. So you can imagine that one team, right, is an example of hundreds of teams, and it's hundreds of models that they have. And another team is just like a very simple model developed by one team. Or not simple, maybe it's complex, but it's developed by one team, right? So at the end of the competitions, right, I think the complex model developed by the hundreds of teams have a slightly higher accuracy of performance compared to the team that's done by 3 or 4%, right? But at the end of the day, if you go do a Google search, right, Netflix actually implemented the model that's developed by these 3 or 4 guys instead of using the model that is done using an ensemble of thousands of models, right? Because the engineers couldn't understand the rationale behind this machine and how the predictions are being done. So this is a real life example of why it's very important to really understand the factors going behind the machine. It's not always the case that if you get 99.99% accuracy, right, the stakeholders will buy in. Like it could be that you can model 75%, right? You can get your stakeholders buy-in. They might choose to use a 75% instead.
Yeah. Understanding model, understanding model interpretability is like one of the new big things. I've seen a couple of new startups that are basically in this space.
Yeah.
And their whole stick is that they are trying to help you understand more of what goes on in neural networks. I think it's called, I can't remember the term right now, but basically,
explainability?
Something like that, yeah. But basically, the whole idea is like, yes, neural networks work great, but like how do you better explain what is actually going on inside, like in those waves, like what's happening? That seems to be one of the big pushes in AI recently. I've seen at least 2 or 3 new startups, like well-funded startups, that just recently popped up and go into this.
Just to build on the point, right? I think based on my experience, right, if you're using very simple traditional model like scikit-learn, like we mostly like decision trees or random forest, right? It's relatively easy to make it explainable, right? Because like by doing a decision trees, right, you can print out the tree chart, like let's say for example, if the age is more than 18, then smoking is allowed. Otherwise, smoking is not allowed. So you can have sort of a layout, right? But I guess in my experience, right, the toughest challenge is when you're using deep learning, right? Especially you're using neural networks. Because neural networks by itself is like it's just a bunch of linear models lumped together, right, to give you that complex model which can mimic the actual real life scenario, and it's hard to explain, right? So Kajun, have you so for your PhD, do you use any deep learning, and do you find it very hard to explain?
For my PhD, because we work with medical data, very small sample size, we didn't use deep learning. That's why we try and use NMF and traditional classification models like logistic regression or SVM. And we also use like gradient boosting classifier. So we avoided the using neural networks. But what Tempo says is true, that it is difficult to explain the behavior of neural networks because when the neural networks learn, usually, even if you, for example, you use a CNN and you're able to look in between each layers, the representations, some of the time is useful, some of the time it's not. One real life example would be using neural networks or deep learning for self-driving cars. And the problem is that when there is an issue with the neural network, it is hard for the data scientists, the engineers to identify the problem in the car, in the algorithm, if it's using neural networks. Because all you do is to just update the labels and then retrain them, and that's not engineering. That's not trying to figure out what the problem is. And then because of that, you might have certain safety issues lah. And so people prefer, sometimes scientists, stakeholders, they prefer models that you can explain the behavior of the models. That's why using unsupervised methods such as hierarchical clustering to actually visualize the tree, or that the clustering kind of calculates, so that you can at least identify the clusters and how the data points interact with each other within cluster and without the clusters.
It's probably much bigger deal for like when it's safety related or medical related, because like you can't explain to someone that, oh, this person died because the decision, like some machine made a decision somewhere, right? Like and there are people that are responsible for that, and like if they can't explain what they're doing, it's very difficult to push things through.
Yeah. So I think one of the ideas that was brought up during a discussion with my friends was like they were saying that, hey, why not when we implement the model, we use neural networks to implement, but when we explain to the stakeholders, we use things like decision trees to explain. So in a way, because the deep learning give you the performance that you need. Because usually deep learning can give you that additional edge in performance, right? But when you are talking to stakeholders, right, so you explain to them using a visualized decision trees to make them understand how the machines are making the decisions. So what do you think about this? Like using one, so I think the general question that I have is like, do you think it's good practice to, let's say, for instance, right, use a highly complex model like deep learning to do the actual predictions? But when you are engaging the stakeholders or to explain the models to other people, you use a much less complex model, but maybe the performance is about very, very similar, just that it's not as good as the deep learning, so that you can get their buy-in and you can visualize the results of how the machine is making decisions. What's your opinion?
I think you must be very clear about what you are presenting, because if you present a decision tree, it seems very deterministic.
Yeah.
And then in practice, if what is actually happening is not following the decision tree, then they're going to come back and ask you what's going on. You show me the decision tree, it seems that, because decision trees are really very deterministic. Like given a fixed input, you always know what's going to come out. A neural network might not always be as easy to kind of explain what's going on, and you have to be very clear when you are presenting to someone that what you're doing it's like I mean you cannot make it seem like you are like that your presentation covers the full variability of what your model is actually doing, because then you're kind of misrepresenting what you are doing as well, and your business guy might be a bit surprised when like he puts in an input and gets something unexpected out. Yeah.
What about you, Kajin? What do you think?
I think you should just present what you want to implement, but you should, in a sense, come up with creative ways to explain why your model behaves this way. Even in academic writing or in academia, when they propose a new, for example, neural network architecture, they do have to present their results and visualizations, plots, like how the loss reduces and things like that, and show, okay, maybe even show the intermediate steps, intermediate layers, of how the model behaves to convince the reviewers that this is a good model, and it's not just based on coincidence that your model performs better than other models. So if you, as in a data science team, data engineering team, come up with a model that works very well, although it's difficult to explain, I think the challenge there is to actually explain how it behaves and why it behaves this way, of course in business sense. And also, I think having good results does in quite a big way validate the use of your model.
Yeah. So I think so that concludes our discussion on the second part of our topics, right, on how important it is for you to be able to explain that, because that ties back to the unsupervised learning, right? Because by definition, unsupervised is that you tell the machine, hey, I don't know what's going on, tell me something about it. When you there are three clusters, right? Let me know how are the clusters being formed. So sometimes being able to explain the model is more important than the model accuracy itself. If you can't explain the model and get people to buy into your model, it's a waste of your effort in trying to develop the model, right? So that brings us to the end of the discussion for unsupervised learning. Because this is the last session of the AMA, right? Ask Me Anything, right? So I thought it'd be good that if you just allocate the last 10 minutes, and we can share some of our career advice on how we get started on data science. Because I understand that most of you on this program, you are looking to either become a data scientist or trying to learn more on your own, right? Because after completing the data scientist courses on the data camp, is not sufficient. So I think we can start with Kajun first. So Kajun, do you have any advice for the participants on the video on how do they get started on this data science journey.
Before that, is there a way to pull up the questions on the chat?
Questions on the chat.
Questions in the chat?
Or the chat, because just now you were showing the chat log, right?
Chat.
Yeah,
Okay.
okay.
I think they're answering it.
Okay, just trying to see what people ask. Better for the questions.
I think it's mostly like models
Technical
related.
kind of
Yeah, but I think you can go generic to just give some career or like inputs.
Okay. So I guess most of you are people who have some working experience who want to learn more about AI, and some of you maybe want a career switch. So I'm very new to AI and only have done the data chem course, right? And you maybe have realized that a lot of the examples in the data chem course are toy examples, and you feel that maybe you don't really understand much about why models behave this way. So my advice would first be to spend time to understand the math that goes on in your algorithms. You can start with simple stuff like logistic regression and behave it that way. No, if you understand the math, it goes a long way, because for example, neural networks are just based on they have a softmax function, which is comes from logistic regression roots, and you have the ReLU activation functions that you have to understand the math behind it. Then if you understand the math behind other things like SVM or even GMM, at least you can understand mathematically how it behaves. You don't need to be like a super genius or like super math guy and know everything mathematically about machine learning or AI. But if you know mathematically how the models behave, you can actually understand the models better, and you can actually say, hey, I can use this model for this problem, because mathematically I can model my problem this way conceptually. You don't need to really come up with very cheap equations, but conceptually you can model your problem and then match it with an appropriate algorithm. And that's if you know mathematically the behavior of the maths behind AI. Another thing would be to work on your own personal projects. Recruiters or potential employers, when they look at your resume, if they just see a data chem course, I don't think it's enough. What they need to see is concrete experience in projects. You don't need to work on super difficult projects, but you can start off by choosing a project that you find interested in, right? You can work on a Kaggle project that has already been done, and try and exploit yourself without copying, for example, the winning algorithm. Or you can think of projects that you can do, side projects you can do, personal projects that you can do, with data that you can easily get. And with that, you can try different algorithms. You can do exploratory data analysis and from there you can understand, why and when you use certain algorithms. You may know theoretically how and why each algorithm behaves, but only when you use it and you try it and you face a problem and you say, okay, how can I increase my classification score, for example, and then you try certain methods and you realize, hey, this works, and you get a feel of the best practices, and you start to think like a data scientist, you start to think like a data engineer in terms of trying to solve the data problem. I think it really helps you understand, helps you get a better understanding of machine learning, and really it will give you an edge over other people in this area.
How about you, Deepan? Anything you want to share?
So I agree with him about projects. I've hired engineers before, and usually what I'm looking out for is past work. Past work is generally the best indicator for future work. If you've done it before, you can do it again. That's kind of, and I mean, the two main things I'm usually looking out for are communication. The soft skills an engineer has are very, very important and often overlooked. Software is a team sport. It's not a solo thing. And the worst kind of engineer is the kind that thinks it's a solo sport, because then it's very hard to get things done. So usually, at least, what we look for is what you've done before, and communication skills. So often an interview might just be sitting down with someone and going through what they've done before and asking them to explain why they made certain decisions. This is from a traditional software kind of standpoint, but I think it transfers over to machine learning as well. In terms of learning, like at least for me, I really like Andrew Ng's deep learning course. I think he does a very good job of explaining the fundamental maths, and in a very approachable way. He doesn't he really starts from the very basics and works up to like works up all the different abstraction layers to for deep learning in these.
Yeah, because like for machine learning, we can get quite intimidated with the math that you see, because people usually just throw everything on the internet. Either that or you don't get enough. Doing courses like Andrew Ng's machine learning course is very helpful, because he starts from the basics and then he builds up slowly, and he touches on a lot of different aspects of machine learning. So if you take that course and you've completed the data chem course, you can actually translate what he teaches in theory into practical software code that you can actually code it yourself and implement, like kind of like a lab session for you, your own. And if you have your own data set that you can choose, you can actually try these things. And like Andrew Ng always says, it's okay if you don't understand it yet. But you can always go back and take a look at the math slowly and try to understand how it behaves.
Yeah. So I think just to bring the session to end, right? So now that you have finished the data chem, right, give you an overview of the various models that you have. But the data chem itself doesn't go deep into the math. So you should continue learning by taking other courses like the Andrew Ng courses that they mentioned to really understand what's going on. So once you have an intuition of the math and how to implement model, then you should try to use the skills on Kaggle competitions to see, like, are you able to translate what we learn in theory and on that data chem to compete in the competitions and see how well we are performing, right? So hopefully, eventually, over time, your ranking will get better with each competitions, because like technically you can just copy and paste your previous code into the next competitions, right? But you build more functionality to it. For instance, like maybe first time around you use a random grid search, but now you know that, oh, there's this thing called random grid search to tune the hyperparameters. Then you put that in. The next time, say, hey, actually I can make use of other features engineering that previously I never thought of. So I think over time, this is how you build your proficiency in developing a better models. And I think this is how you can get started on your data science journey. So that brings us to the end of the AMA. So on behalf of the everyone from AMA team, thank you for your participation and for dialing in, even though this is the last video recording for the AMA. I hope that you enjoy our engagement and our discussion with you, and hope that you learn something from this session. But all the best. Thank you.